Okay, so the next thing for part two of dot products and vectors is talking about the angle between two vectors. And the angle between two vectors is the cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. So when you think about it, if you have, so how does this like, what are we talking about? When you got to visualize that if you have two vectors, so in the coordinate plane, if you have two vectors, let's say you have a vector, like, all right, say you got something like this, and you got one vector going this way, that's a big one. And you got another vector going that way. So I don't know, we'll call this vector u and this vector b. There's an angle theta in between them. And that angle theta in between them that we want to use is is found by the cosine of theta equals u dot v over the magnitude. So let's try a sample problem using that principle, that idea. Okay, so find the angle between the two vectors u and v. So to find that, it's the cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. So if I do that, well, the dot product, I believe the dot product of that is, so how's it go? It'll be 3 times 1 plus 2 times 0. That's the dot product over the square root of 3 squared plus 2 squared times the square root of 1 squared plus 0. So what does that come out to be? The numerator, so the cosine of theta is equal to 3 over, was that radical 13? Because 9 plus 4 is 13, and that's 1. So there's that. Well, how do you get theta? Well, theta is found by taking the arc cosine of 3 over radical 13. And you punch that in the calculator. And if I punch that in the calculator, I get something of like 33.7 degrees. So that's the angle that's between, if you kind of check this out, it's like, here's 3, 1, 2, 3, 1, 2. That's that guy. And then 1, 0. That's that guy right there. So that angle right there is 33.7 degrees that they make. All right. So how does this play into what we're talking about? Next thing that you need to know about is what's called um, orthogonal vectors. Okay, orthogonal vectors. Well, what are orthogonal vectors? Orthogonal vectors are just like if you have two vectors, and if you take their dot product and you get 0, you get what's called orthogonal. So basically, what do you mean by orthogonal? Well, that's basically the term orthogonal almost means the same thing as perpendicular. So the 0 vector has no direction angle, so technically speaking, the 0 vector is not perpendicular to any vector. However, the 0 vector is always orthogonal to every vector, except for um, the case I just mentioned. So essentially, orthogonal is just like fancy talk for perpendicular. Okay? So if you take the u dot v, if that is 0, then they are orthogonal, which means they're almost perpendicular, which means they're almost at 90 degrees. Okay, so let's talk a little bit about that. So if I say like something like prove that this vector u and this vector are orthogonal. If I say prove that they're orthogonal, well, we're going to just do u dot v. So if I do that, that's going to be 2 times negative 6 plus 3 times 4, and that's negative 12 plus 12. So since that I have that the dot product is 0, I've proven that they are in fact orthogonal. Does that make sense? I hope. Good. Let's talk about the next thing. Talking about when you project one vector onto another. This is very bad, so I will write it out better. So before I get to that, we'll talk about it. So a vector projection kind of looks like, well, let me just say, so if you have a vector projection, um, you basically drop a perpendicular and you have a resultant vector. So what is all this terminology? Let me just draw a picture first. So um, I guess what I'm going to say is, let's say, for example, I have, we'll call this u, but this is a vector pq. Okay, this is a vector pq. Okay, and I have another vector. This is going to be ps. Okay, so I got vector pq and I have vector ps. All right, and we'll call this part v, just so I don't have to say it so much. All right, if I drop a perpendicular right here like that, right? If I drop a perpendicular from Q to PS, I have a new line or a new vector made, so to speak, and that's new vector right here is right here. We'll go like that. That guy right there, we'll call that R. That vector is PR. What we've just done is a vector projection. Okay, so the vectors U and the vectors V have a projection, whatever that PR is right there. So I guess that would be PR would be the projection U onto V. That's how you write it. The projection U onto V. So basically it means like this guy. Projection U onto V means, when you're the first part, the projection U means that's the guy you're dropping the perpendicular on. V would be the one that receives the perpendicular the perpendicular, if you will. So the formula for calculating the projection, in this case, if I want the projection of U onto V, that's going to be equal to U dot V over the square of the magnitude of V times V, the component vector. All right, if that makes sense. Hopefully. Let's try. You know what? Let me add something. Let's try one real quick so you can kind of get an idea of what I'm talking about when I say this. So here I have this. I have vector U, which is going to be 6, 2, and I have vector V, which is 5, negative 5. So what I have, I want to find the vector projection of U onto V. So what I want to find is, I want to find the projection of U onto V. Now what is that going to be? Well, that's U cross V over the magnitude squared times the component. All right. So next thing we do is see if we find the U dot V. So U dot V is going to be 6 times 5 plus 2 times negative 5 over, and oh, that's kind of like I can do V dot V, so I'm going to do that real quick because I'm going to pinch. So 5 times 5 plus negative 5 times negative 5 with 5, negative 5. So 30 plus negative 10, that's 20 over 50. That's just a scalar times 5, negative 5. So that's 2/5. So that's 2/5 of 5, negative 5. That becomes, the new vector is going to be 2, negative 2. So how does this all look? What does this look like? Okay, well, this is what it looks like. All right. First guy, 6, 2. 2, 3, 4, 5, 6, 1, 2. And so it's going to go way out like that-ish, roughly. That's U. And then V is 5, negative 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Come way out like that. That's V. If I draw that perpendicular thing down like that, my projection vector is this guy right here. That's the new one, because that's the 1, 2, negative 2, if that all comes into play. Now, where is this applied in the real world? Well, that's an awesome idea. Work. The force is a constant force whose direction is the same as the direction of AB. Then the work W done by F in moving an object from A to B is that right there, the magnitude of F times the magnitude of B, or magnitude of AB. I'll show how this works in class. All right, we'll spend a little bit of time on that probably in class tomorrow. So hopefully this makes sense, and may the force